Hi there audiophiles, OCA here. This video will be about speaker crossovers, how they split the audio signal between the speaker's drivers, why they introduce phase distortion, and how to fix it with Mini DSP. If you don't want to allocate your limited FIR taps for this correction, or if you own an older model of Mini DSP, a detailed explanation of how to correct crossover phase shifts with just BQAD filter coefficients will also be given.
Speaker crossovers are electronic circuits that divide an audio signal into different frequency bands to direct those frequencies to the appropriate speaker driver. In a passive multi-way speaker, these analog circuits typically use a combination of passive components like capacitors, inductors, and resistors to create filters that block or attenuate certain frequencies while allowing others to pass through. Analog crossovers begin with a resistor and a capacitor. Resistors dissipate energy without frequency prejudice. All frequencies are treated equally. Capacitors, on the other hand, selectively absorb energy. They store it, to be released at a later time. While resistors react instantly to any voltage changes within a circuit, capacitors take time to charge and discharge. Direct current, think of it as zero frequency, will not pass at all, while at the other end of the spectrum very high frequencies will not be absorbed and capacitors will act like a piece of wire. The diagram shows such a crossover network. By interchanging the positions of the resistor and capacitor, low-pass and high-pass filters can be obtained. For the low-pass case, LF, the capacitor ignores low frequencies and shunts all high frequencies to ground. For the high-pass case, HF, the opposite occurs. All low frequencies are blocked and only high frequencies are passed. This is how frequencies will be divided between the woofer and the tweeter of a typical speaker. Because there is only one capacitor and one resistor in the circuit, this is a first order, also known as first-degree crossover. Each order of a crossover network applies a 6 dB per octave attenuation on the frequency band. That means the volume is decreased by 6 dB when frequency changes by a factor of 2. A second-order high-pass crossover at 5000 Hz will cut the volume from 5000 Hz to 2500 Hz by 2 times 6, 12 dB, hence is said to have a 12 dB per octave slope. The combination of a low-pass and high-pass crossover at the crossover frequency applied to LF and HF drivers respectively will give a reasonably flat overall frequency response. However, crossover effect is not limited to only the frequency response. A crossover network will also cause phase shifts proportional to the order of the filters due to the energy-storing nature of the capacitors. Each capacitor in a circuit contributes a total of 90 degrees of phase shift, which is audible as a time delay between frequencies before and after the crossover frequency. Correcting for these crossover phase shifts is important because it helps to ensure that the different frequency components of the audio signal are properly aligned in time and phase. This results in a more accurate and natural-sounding reproduction of the original sound. By minimizing phase shifts, it will decrease group delay, which is the first derivative of the total phase shift along a frequency band. It will also help raise the sound stage higher because when time-aligned, lower and higher frequencies will tend to form the acoustic center closer to the high-frequency driver.
We will create the BQAD coefficients necessary to correct crossover phase shifts in perfect Mini DSP format in 3 steps. First, let's create a crossover phase correction by using the filter linearization tools in the excellent free tool Rephase. Import a speaker measurement created in the Room EQ wizard and export it as text. Go to Filters Linearization tab and list the speaker's crossover frequencies. This measurement belongs to a 3-way Focal Canta 2 floor standing speaker. It is a 4th order, 4th degree crossover at 2700 Hz, which divides the audio signals between the mid-range driver and the tweeter. Thanks to a lab test report by Stereophile magazine, I know this is a Linkwitz-Riley 4th order crossover filter. So we need to apply 4 times 6, 24 dB per octave correction. Here, as you see, these are also Linkwitz-Riley. However, the phase doesn't seem to be at 0 degrees. It's exactly the opposite, drifting at the extremes between minus pi and plus pi in the wrapped phase graph. What we need to do is invert the polarity of this correction filter, which we can do here. So it's an inverted crossover filter there, polarity inverted. Next in line is the crossover at 260 Hz. Which divides the frequencies audio signals between the woofer driver and the mid-range driver. I don't have information on the type of this filter, however it seems to be most flat at 12 dB per octave. 24 seems to be too much. When you use keyboard up and down cursor keys, you can bring up temporarily this yellow vertical line, which will show you the frequency 260 Hz. And you can see it's sort of close to 0 degrees, which is the perfect phase response here, 0 degree axis. Finally, there is the port phase shift we need to take care of. Here you can use the box filters. Vented types are for ported speakers, these three, and closed types are for sealed speakers or subwoofers. Again, thanks to Stereophile's report, I know that my combined port frequency for the speaker, which in fact has both a rear and a front port, along with an additional passive woofer, is at 41 Hz. Low Q vented seems to be the best match among all these. Before this, as you can see, there's a phase slope going upwards like this here. And this one just tames it, brings it closer to zero axis. And in fact, this vented low Q filter is nothing more than a 24 dB per octave. As you can see, same effect linked with Rayleigh phase linearization. The normal way is quite complicated, as you see, polarity inverted all three of them by coincidence. And if you pseudo align the timing here of the speaker, bringing the highest measured frequency to axis 0, which arrives first to the microphone, it's pretty flat now throughout the frequency band. So this seems to be my phase correction. It's not a straightforward process to find the correct phase correction parameters, especially in multi-way and multi-port designs with high filter orders like these Kantas. You will need accurately time-aligned impulse responses of your speakers, and especially for the box filters, you might need near-field measurements. I have explained methods for most of these in my previous tutorials, so I will not go into these details in this one. At this stage, let's create the FIR filter to correct this speaker's crossovers and box phase shifts. With unlimited taps of modern convolution engines, you can perfectly replicate the correction. Let's say we have 16,384 taps, 48,000 Hertz sampling rate. Let's keep it at mono at 32 bits IAAA and call this crossover and box phase correction. Generate, and as you see, apart from this area at 10 Hz-ish, which is inaudible, it perfectly replicates. If I increase the number of taps to 65,536, generate, now it's almost perfect everywhere. And without any windowing and centering or optimization, we can easily create a FIR filter convolution file for correcting all the phase problems of the speaker. But if you have a mini DSP which accepts FIR filters, your limit is usually 1024 taps in 2x4 HD model. And with that one, now let's clear everything. Reset settings. No. Now you have 1024 taps, and let's say you have the same crossover linearization filters is necessary, one at 27 Hz and one at 260. One is 12 dB per octave, the other is 12. So this is the phase shift that needs to be applied to the speaker. As you see, no effect on the frequency, and I'm excluding the box correction for this time. Mini DSP HD accepts 96 kHz, and it has to be in 32 bits IAAA binary format. And if you create that with 1024 taps, you will see that the phase is almost perfectly matched, but it had to change the frequency response. It almost 1.4 dB lowered the volume starting from 500 Hz downwards. You can optimize that with rephase. Let's use moderate optimization. Optimization, by the way, only optimizes for the frequency response. And while correcting that, optimizing that, it will compromise the phase response. So it's a two-way street. While trying to optimize frequency response, you can ruin the phase correction. So let's give this a try. As you see, it's now fixed the problems in the frequency response. It is what it needs to be as a phase correction with no effect on frequency response, but it increased the difference between the perfect phase and the phase it will be applying by 1024 taps, but it is still very acceptable actually. In high frequencies, no problem at all, and starting from 500 Hz, just like a 1 degree difference from ideal. It's not a big deal. And if I use, for example, rectangular windowing and generate, as you see, it's even better now. It's almost perfect. And with rectangular, you can go down to even 512. Well, it's a little bit less, and you can always stop the optimization. If you click stop button, it will stop at the best that it found until that point. Then you can use maybe energy centering for rectangular. No, look, I'm gonna now stop because it's not improving. Okay, this is, for example, causing a delay of 2.66 milliseconds here. If you are okay with 5 milliseconds of delay, which is inaudible to human, then generate a delay with 5 milliseconds. As you can see, with even 512 taps, we managed to perfectly replicate this phase correction up to 20 Hertz. There's a little difference here. So you're flexible here. In fact, even with Mini DSP 2x4 HD, you can use 2048 taps in just one slot, and you can use the remaining 3 channels for the remaining 2048, a total of 4096, I think. And with Flex, you have 6144 taps. So it depends on the model, but it's always the same format. And now let's assume we also had this box correction at 41. Then even with 2048 taps, I think, as you will see, with low frequencies, lower taps are horrible. It will have problems. It's possible to optimize this better, but it will never be perfectly matching the phase and the frequency response together. If I don't optimize the frequency response, it will be a better phase response, at least here. But look at what happened to the frequency. 6.5 dB drop in the low frequency volumes. So the advantage of biquad filters is that you can use these with no problem. The lower frequencies that you cannot touch with no matter how many FIR taps you use. I mean, to correctly mimic something like that, you will need at least 16,000. Or maybe if Flex can do this properly. Let's try. Unfortunately, no. Okay, maybe middle and this. Yeah, Flex can do it. So the box filters work too low down the frequency band for 1024 taps to ever be sufficient. It's an additional advantage of using biquads. You can easily apply this filter with biquads to the very same Mini DSP. Or in my case, I use a balanced 2x4, the very first model of Mini DSP, and it doesn't even accept FIR filters, only biquads. Now, in this second step, I will show you that these rephase linearization tools are in fact time-reversed all-pass filters. An all-pass filter by definition is a combination of a low-pass and a high-pass filter, thus no effect on the frequency response and only affects the phase response, and is used for phase correction mainly. A nice feature of rephase is that you can open multiple instances of it working independently from each other. I want to again reset, otherwise you can't get rid of these red and blue lines. Okay, now 260 Hertz and 12 dB per octave. So this is the phase correction this phase linearization tool is achieving. Now let's go to minimum phase filters and let's pick the shape. Look, you can do high pass and low pass. And you can also pick here all pass. In fact, all pass should be, as you see, the type has been grayed out because it's neither high pass nor all pass. Ideally, all pass should be here, and here in the shape you could choose first order or second order. But anyway, let's enter the frequency at 260 Hertz. As you see, it's quite different. Why? Because this, in fact, is the crossover at 260. This is the crossover working in the speaker. To counteract this phase shift that this is causing at 260, there is this twist, and there is like a 1 pi movement throughout the frequency band from pi to 0. This needs to be time reversed so that it compensates for this phase shift. And time reversing you can do here, time inverted. And when you do that, as you see, it's exactly the same filter as the phase linearization tool of rephase. So this is actually nothing more than a first order all pass time reversed. Okay. And another way to time reverse the filter is using this compensation here. This is also compensate mode, is time reversed. So you can selectively time reverse some of the filters and don't reverse some of them if you really need to for some exotic corrections. Anyway, now let's go and check for the other one, the 2700 filter. This is its shape, minimum phase again. Let's make it normal and let's choose second order all pass and 2700. But these are again needs to be time inverted. As you see, they are identical now. So the fourth order Linkwitz-Riley filter in my speakers crossover can be compensated by a second order all pass with a parameter of 0.707, and this is also flexible. This is, by the way, 1 divided by square root of 2 for certain reasons. That's a Linkwitz-Riley constant. When Q is this, it equals the fourth order Linkwitz-Riley. By changing the Q, you can try many different shapes. And again, as we mentioned before, a box filter is nothing other than a second order all pass, fourth order. So let's add this box filter here, low Q 41, and time reversal is still invalid here, so they're identical. Or you could time reverse it here, it's still the same thing. So it's either a first order all pass or a second order all pass. One other advantage, okay, for example, in this one, when I applied all the corrections, let's say it wasn't and polarity inverted. Let's say this one is not perfectly at axis 0. Instead of using this one, you can just as well go to minimum phase filters and frequency 41, port frequency, second order all pass, and time reversed, and just play with the Q constant and make it perfect for your speaker. So instead of 0.7, in fact a Q of 0.6 could even be a better match for my speaker, and I could just create a convolution file with these settings. So this is one more trick. Also here, remember that we had to invert the polarity. So after creating, for example, this filter and another one, first order at 260, let's keep them normal for now, and another one, second order at 2700, all these three, even ideally this should be 0.6, and time invert them and polarity invert them. So this is equivalent to the filter I created in Rephase with filter linearization tools. If I clear the measurement, as you see, they are identical in every way. Now the third and the final step is the creation of biquads for these time reversed all pass filters.
Biquads are computationally efficient and can be implemented using simple arithmetic operations. The term biquad is short for biquadratic, and they are second-order infinite impulse response filters. They are called biquads because they have 2 poles and 2 zeros in the transfer function. A transfer function is a ratio of 2 quadratic polynomials, and biquads are simply the coefficients of these polynomials. The coefficients in the numerator are the zeros b0, b1, b2, and the coefficients in the denominator are the poles a0, a1, a2. Please note that a0 is the coefficient associated with the filter's output, and to normalize a filter, one needs to divide every other pole coefficient by a0 so that a0 becomes 1. Mini-DSP will accept only normalized biquad coefficients.
One way to calculate biquad coefficients is to download the Excel file from the Mini-DSP website. It will calculate biquads for many types of filters. The name is All Digital Coefficients version 1.2. From low pass filter, high pass filter, band pass filter 1 and 2, notch filters, peaking, EQ, low shelf, high shelf, and this I think for Winley, RIAA, and there is also all pass filter. But it only covers the second order all pass filters, so you cannot replicate a 12 dB per octave linearization, and they are not inverted in time, so it cannot be used for filter phase shift compensation. So I created a new Excel file for this purpose. Here are some basics all pass filters for biquads. The calculation is quite easy. This is first order and this line is second order. This is the central frequency, the frequency at which you're going to apply the filter. Let's say 260 Hz, and this is sampling frequency 48,000 or 96,000 depending on your Mini-DSP model. A0 should always be 1 with Mini-DSP. They should be normalized, so you can't even enter A0. You have only A1, A2, B0, B1, B2, 5 coefficients that Mini-DSP will accept. Formulas are quite simple. I won't go into the details of that. And for second order, there must be a quality factor, bandwidth. This number here is the square root of 0.5, 1 divided by square root of 2. This is the Q coefficient, very commonly used. So I have a copy of it here in case you need, quite precise. So for the first order all-pass filter, which you will use for 12 dB per octave correction, all you need is this constant here, tangent of pi times frequency divided by the sampling rate. And this tangent actually is wrapping it in the Z plane, but I won't go into details of any of that. And when you polarity invert a B-quad filter, the B coefficients change sign. As you see, the A coefficients are the same as the original, and the B coefficients are multiplied by -1. So plus 0.96 becomes minus 0.96, minus 1 becomes 1, and 0 stays 0, of course. To time invert a filter, you have to exchange the places of the A coefficients with B coefficients. Okay, these are pole coefficients, these are zero coefficients. So you change the poles and zeros of a filter and you invert the time for that filter. So here, for example, the A coefficients 1 minus 9.66 move to B coefficients, and the B coefficients here move to A coefficients, and this is time inversion. However, when you time invert B quads, A0 is no longer 1, and you cannot enter it this way to mini DSP. You have to normalize them, and to normalize them, you divide every A coefficient with A0. So A0 becomes 1 here. You're dividing this number with itself and it becomes 1, and then you're dividing -1 here with this number and it becomes this, and you divide 0 with this number and it stays 0. You don't touch B coefficients, they stay the same. So now, as you see, A0 is 1 and we no longer have to enter it to mini DSP, and it's normalized and time inverted. And to polarity inverted, time inverted B quad, you just simply change B coefficient sign as above, the same thing. A coefficients stay the same and B coefficients change their sign. Same goes for the second order. You just use the Q factor here, and the formulas are a bit more complicated. As you see, these are the formulas. This is for the basics of B quad calculation. You don't need to know any of that. Here I made 8 B quad filterization. You will simply enter the sampling rate here, which should be the same for all filters, and center frequency here. Whether or not you're going to invert polarity. When it's 0, polarity is not inverted. When it is 1, it's polarity inverted. And quality factor, if you enter any number here, then it's a second order all pass and it will calculate accordingly. If there isn't anything here, it will calculate a first order all pass. Okay. And I also put the inverse of square root of 2 here if you need to copy paste the number to any of these boxes. Let's go back to Rephase. To load Rephase previous settings, I will show you a small trick. Here are my Rephase settings. You just copy them and you can load settings from clipboard, and all the settings are here. Rephase can save settings as a string like that, and you can just use the clipboard. It's quite handy. So the filter linearization for my speakers, 1 fourth order Linkwitz Riley at 2700 Hz, 1 second order Linkwitz Riley phase correction at 260 Hz, 1 for the box at 41 Hz, again fourth order, and all of these are polarity inverted. These are the phase correction for my speakers crossovers and the ports. So with the Excel file, all you have to do is enter these filters here. All of them are polarity inverted. So 1, this stays the same. When you have a Q value here, it understands it is second order, so it will be a 24 dB per octave all pass filter, second order actually, which is the required correction for fourth order Linkwitz Riley. And the second one is at 260 Hz. Again, polarity inverted. By the way, for example, with Rephase, you can only polarity invert either all of the corrections or none of them. Here you have the possibility to selectively invert some of the corrections. you might need that kind of correction, you never know. I will delete the quality factor because this is a first order all pass. As you see, it has only B1 and A1 coefficients. And the last one at 41 Hertz, again polarity inverted and again second order. So I copied this number here. In fact, we found out this to be 0.6 if you remember, for better match. So I have these three filters. If you needed to apply, for example, 48 dB per octave correction at 2700, you just go and add another second order all pass. As a B quad, and now it's a total of 48 dB per octave at 2700. When you delete this frequency, it's not gonna calculate any B quads for it. In this way, you have up to 8 B quad coefficients. Why 8? Okay, here it will automatically create the required B quad entry for your mini DSP in the format that it will accept. As you see, there is no A0. This is the format, and this comes automatically from this table, so you don't have to do anything here. Now let's go to mini DSP. Okay, for example, my mini DSP 2x4 balanced, the very primitive old mini DSP, has 5 B quads here for parametric equalization and another 5 here. Okay, and these are the crossovers, but the crossover filters in fact have capacity to accept 8 B quad filters. You have 5 here and 5 here, 10 and 8 here, 18 separate all pass filters or B quads you can enter in just one channel. Even in the oldest, simplest form of mini DSP, even for the lowest frequencies, you can add corrections. It's very easy. This is the basic form, and the advanced format, it will be empty, and you just paste what you copied from the Excel. As you see, it's here from B quad 1 to B quad 8. You have to always enter these B quads even if they are 0, so you can't just cut short. But if you're gonna add this to, for example, the parametric equalizer, it accepts only 5, so it should be something like that here. Let me try. And the last one I think shouldn't be. And process, I don't know it. Well, you have to enter here one by one, unfortunately. It doesn't accept all 5 at once, but there is a limit of 5 B quads here, and they can all start with B quad 1. It doesn't matter what you see after processing. This was empty, that's why. Okay, now this is limited to 5, which will not be accepted. Let me do it one more time. Copy and paste here and process. And the processing goes without any problems. As you see, there is only a thin green line here at 0 showing the frequency response because there is no change in frequency, but the phase response is corrected as required at the end of this correction. And then you upload it to mini DSP by clicking this button. That is all for the B quad calculation and entering into mini DSP. And before I end this video, I want to just show you quickly why fixing crossover phase shifts and box phase disturbances is so important. The red line here is the phase rotation. It's in three-dimensional space and it's quite complex. The green plane is the imaginary plane, and that's the imaginary component of this phase rotation. The yellow plane is the real plane. This is the real component of this phase rotation. And the black plane at the back is the polar plane, where you have the unit circle. So it's quite complex. That's why it's quite hard to grab the phase rotation idea in a wrapped 2D graph or unwrapped version, as it were. And lastly, this is the relationship between a phase shift. The red line is the phase, making a 360-degree shift here from plus pi, 180 degrees, to minus pi, and then smoothly going back to 0 at 1000 Hertz. This kind of phase shift, for example, causes a phase delay of this much, 0.51 milliseconds. This is the phase delay, time delay, literally, in milliseconds. And the group delay it will cause is this one. As you see, the peak of the group delay is not exactly on 1000 Hertz. and the peak of the phase delay is not exactly on 1000 Hertz. They are on opposite sides of 1000. What you should remember from this graph is that this is a crossover causing a phase shift at 1000 Hertz. And look at the group delay it introduces. So when you apply the opposite of this time reversed version of this crossover phase shift as a filter linearization, you apply the reverse of this group delay. So you literally decrease the group delay by 0.69 milliseconds at around 1000 Hertz. And group delay is one of the hardest things to get rid of in any digital correction. So this very simple correction with no frequency magnitude correction involved gives a much cleaner sound overall, because it gets rid of the group delay as much as it should be remote. So that's all for today, folks. I hope you enjoyed the video. Don't forget to subscribe, and bye until the next time.